Okay, everybody, welcome to class. Happy Wednesday. We will get started in just a moment. Let's first review our learning objectives for today. We'll see how much of this we actually get through. We'll probably spill over to Friday. But we're going to introduce, material science has just some awesome terms like crazing. We'll learn about crazing today. There's many more to come this semester. We're going to talk about fatigue testing. We'll deal with sample variability and how we actually treat that as engineers. More to be said about that in a few chapters. We'll talk about what exactly crack propagation looks like and how we can model it, which is pretty slick. If we have time, we'll get to the latter half of the class and talk about creep, another fantastic material science term, steady state, creep strain rate, and maybe even accelerated testing. That's probably Friday. So we'll pick up where we left off last time. Let's just quickly review. Last time we introduced Griffith fracture toughness. Griffith's fracture toughness works for brittle materials, right? Some materials that you don't think of as brittle might actually behave in a relatively brittle fashion. Some steels, for example, you can use this equation for. Now, the equation works by setting a material constant that we call the fracture toughness. And even though I'm calling it a constant, it depends on things like strain rate and temperature and grain size and lots of things about the material itself. But the point is, once you manufacture material, you could list what K1C, the fracture toughness, is under different scenarios. And then you as engineers can use that. You could look it up on that spec sheet and say, okay, if that's my fracture toughness and I want to avoid fracture, then I've got a couple options. If I can't control the stress that it's going to be under, right, if you know that no matter what you do, it's still going to see at least at most, maybe is a better way to put it, 300 megapascals, then you can design for what the minimum flaw should be in order for this thing to be used safely. And then you could actually test for that thing. Oh, hold that thought. Hold that thought. I've got a really slick demo. Dang, I think I forgot to do it. Give me 1 second. Okay, wait for it. It's worth it. This will be slick if it works. Okay, while this is pulling up, anybody seen the show Diesel Brothers on Discovery Channel? A couple random people. So this is my little brother's show, actually, which is kind of cool. And they did an episode that fits right. So on the show, they had just bought this completely ridiculous rock crawler, and they wanted to know if whoever made this thing had actually done a good job of building the structure, like the roll cage that went around it. So they bring in a local testing company, Quality Testing Instruments, QTI, I can't remember what it is, some company, and let's see what they do. Hold up, let me turn on the volume. Quality Testing and Inspection, that's it. Can you not hear it? I don't know where the volume is. But they're essentially, what they do here is they're able to visualize each one of these welds where they come together because they take a little plaque that it's sensitive to x-rays essentially. They shine x-rays on it just like when you go to the dentist, right? When you go to the dentist, they've got that awful thing that they put in your mouth, and then they've raised the camera right next to it and they snap a picture. And what it's doing is it's bombarding your face with x-rays, right? And x-rays are able to pass through a lot of materials, but they get slowed down or absorbed by some materials. Like in your teeth, if you have a nice healthy tooth, it should be absorbing x-rays. But if you've got a hole in your tooth, right, a cavity forming or a crack or something, they can see that because the x-rays go right through it. So they're doing the exact same thing here. In this episode, they're able to, I don't know where our volume is, but they're able to essentially examine these welds, and they can find spots where they didn't adhere well, where there's pockets, where there's air bubbles. Basically, anybody who's welded before, you know, you're basically controlling a tiny little arc of electricity that's melting locally your material, and if a bubble forms, it might look fine from the outside, but believe it or not, that's my little brother. He's like this big. So they can see tiny little holes in the material. So this is the exact sort of thing that you could do if you wanted to figure out what's the biggest flaw in your material, right? You could actually measure it and say, oh, there's a flaw in this weld that's a millimeter big, and you could use something like Griffith's fracture equation to predict whether or not it's going to fail, okay? So that's X-ray. You can also do it with ultrasound, which basically takes a pulse of sound, right? It takes vibrations. It passes them through the material, and if it hits a defect, it'll bounce back to the receiver faster than if it were to travel all the way through the material, right? That would bounce back later, and so they can actually detect flaws in material. So there's lots of what are called non-destructive testing, ways to find flaws in your material, which is great because oftentimes maybe we can't control the stress. We know that it's going to reach some level, but we can test to see whether or not our material is going to fail, okay? Any questions about Griffith fracture toughness? No? Straightforward? Okay. All right, so let's talk a little more about fracture. So ceramics, when they break, when they fracture, it's almost never plastic. And there's exceptions to every rule. But ceramics, by and large, you've experienced this. If you take a dinner glass, a ceramic glass, and you try and bend it, it's just going to fracture. A plate is going to do the exact same thing. There's something called slow crack growth that's possible. Slow crack growth is interesting. You start out with a crack maybe on the surface, right? Chalk is a ceramic. You could start out where if I try and bend this, it doesn't break. But if there's a crack on the surface, right, if I notch that with my fingernail, and then I expose that to water, the whole ceramic chalk is going to start to dissolve in water, but it's going to start to dissolve most rapidly at the tip of that crack. So we call this stress corrosion cracking. When a crack grows differently because of the environment around it, that's the corrosion part of it. So it's not an electrochemical corrosion. This is a physical change. And what happens is that when you've got a tip of your crack, right, so you've got your material, has some cracked tip, right, so this is your material. At the tip of that crack where you have a very high radius of curvature, the chemical potential is different at the tip of that crack than elsewhere in the material. Somebody remind me, what was chemical potential again? Anybody remember this? It was that mu symbol. Basically, it's the change in free energy as you add or remove a single atom. So think about dissolving this. That's basically removing an atom. The chemical potential tells us that the energy associated with removing an atom is different at different parts of this. And it turns out to be really high right at the tip of that crack. In other words, it's beneficial for it to dissolve the material at the tip of the crack rather than the other areas. Or if it's going to dissolve everywhere, it's still going to dissolve along this tip faster. So if that continues to dissolve, this crack will continue to grow over time. Sometimes you can actually see this happen really quickly. If you have a quartz tube and you want to break it because you need to cut it, you can actually put it in a tile saw, a diamond saw, and you can cut through it if you want. Or you can actually just scribe it. What's a scribe? It's just a diamond, right? A sharp tip of diamond, and you scrape it along the edge, and then you can cause that thing to break. You can try and break it with your hands, but it actually gets much easier to just lick your finger and you wipe it along the edge of that crack, the score that you just made, because the liquid right there goes into that crack tip and very rapidly starts to dissolve right at the crack tip, and it will actually break, at half the level basically. So it's much easier to crack these things. So be aware that this is something that can happen. It's mostly something we care about with ceramics, this stress corrosion cracking or slow crack growth. So fast crack growth is like what I just described. If you lick that thing and it pops, it breaks. Slow crack growth could happen over a long period of time. Maybe it's years or months. So on day one, when you made your device, everything was fine. And then a month later, all of a sudden you see that this thing failed and you think to yourself, well, I never changed my stress condition, so why did it break? Well, if it breaks, one of two things had to happen, right? The right-hand side of this equation had to overcome the left-hand side, which means either your stress went up, something happened to your geometry factor, right? Or your crack grew. And so that slow crack growth can happen. We'll talk more about how to model crack growth by the end of today. Typical values you should be aware of. Fracture toughness for metals is something like less than 10 megapascal root meters. Even that ceramic knife I showed you, which is relatively speaking very tough for a ceramic, probably doesn't have a fracture toughness in the 20s. It's probably teens at best. Whereas metals, aluminum, steel, these things are 20 to 80. If you look in the back of the book, it has lots of tables, but they're many, many times tougher than ceramics, which is why they don't break brittly. Okay? Let's keep going. Something worth noting is that ceramics almost always fail under tension. they almost always fail under tension. You can make them fail under compression. If I made a little, cylinder and I squeeze on it, pure compression, it will fail, but it fails at something like 10 to 15 times lower stress under tension. And so it's far more likely that ceramics break under tension. So if you're bending it and you've got the compressive side and the tensile side while you're bending this thing, it's always going to break on that tension side. Okay, polymers can also fracture. A lot of polymers that you can think of, maybe think of like silly putty. You can just stretch this stuff and it's not fracturing anytime soon. But some polymers can be much more brittle. The yield strength, that's the sigma y, the stress at which they start to deform is typically way lower than a metal or a ceramic. You've seen this. If you take a plastic bottle, you can bend that thing really easy. But it takes a lot of strength to bend the exact same dimensions of a glass or metal, a glass or a ceramic. Sorry, glass or metal. There's different types of polymers, which we will discuss later. There's thermosets and thermoplastics. We'll get to these in a few chapters. Thermosets are things that don't melt when you heat them up, like epoxy, right? An epoxy, if you heat it up, it will just burn. Whereas polypropylene, if you heat it up, it will melt, and you can actually recast it again, okay? So these things are going to behave differently. Thermosets tend to be brittle, right? And thermoplastics tend to be ductile. All of these things depend on temperature. We showed you how a banana, which is just a bunch of different polymers, was able to fracture under brittle versus ductile conditions as we changed temperature and strain rate. And so you can do that with basically all polymers. Something interesting that happens with polymers is this terminology of crazing. Crazing happens when a crack forms, but material bridges across it, right? If you look in this, as this thing's being pulled apart, a crack is formed, but in this microscopy image, you see little tiny bridges forming across that. So I think this is our first question. First clicker question. Will polymer crazing increase or decrease fracture toughness in polymers? Should this increase the fracture toughness or should it decrease the fracture toughness? Okay, so get your answers in. We're going to close the poll. Okay, closing the poll. Okay. People think, vast majority of people think that this will increase the fracture toughness, right? Or in other words, when we say the fracture toughness, that's the left-hand side of the equation. That's the K1C. So bridging, that's going to make it harder for this thing to fracture because you've got little things bridging the gap. Or in other words, in order for this thing to continue fracturing, you're going to have to snap all these little bridges, which made it tougher, right? So this is a way to increase toughness. And this is one of the reasons why plastics often, and not all plastics, but many plastics, are surprisingly tough. Relative to ceramics, they are tougher typically, many of them. Yeah, Eric?
So was the question saying that when you have those bridges versus when you don't have the bridges, or when you have the crack and the bridges versus when you don't?
Oh, yeah. So the question is, crazing is this, when you have the bridges.
No, but does crazing increase the fracture toughness relative to no crack or relative to crack without crazing?
I think it's either way.
Either way.
Yeah, either way, it still increases it.
But shouldn't there's more stuff together and bonded when you don't have a crack at all?
Oh, relative to no crack at all. Yeah. No, this is fracture toughness. Fracture toughness assumes that you have a flaw, right? Fracture toughness, we go back to our equation up here and you say all things equal, the exact same flaw A, the exact same stress, will it be the same? No, because one has a higher resistance to fracture. That's the fracture toughness. Yeah, Jordan, no. Jaden.
So crazing only occurs in polymers?
So you can get things that look like crazing, where there's crack bridging in lots of other systems, mostly composites. So many of you mechanical engineers hopefully are going to go out and work in the industry making composites. maybe glass fiber, right? Carbon composites or glass fiber, fiberglass. All of these things have high toughness because they have two phases. You've got your matrix, and then you've got something in the matrix like fibers or strands of carbon fiber maybe, and those can bridge gaps really well and prevent fracture. So they have high toughness as well. We'll talk about composites. That'll be the last chapter we cover this semester. Yeah.
So is crazing kind of automatically happens?
Yeah. Polymers and crazing is nice because it's sort of something that naturally happens as polymers deform. Why do you think it happens? Why does crazing happen? It doesn't happen in metals. It doesn't happen in ceramics. What do you think? Doesn't have to be shear stress that causes it. You can get this under pure tensile loading. What's happening here? Josh? Yeah. Yeah, what is polymers? Go back to what our picture was earlier in the semester. It's a bunch of spaghetti noodles in a bowl, right? As I'm pulling that apart, I'm grabbing two chunks of the noodles, and I'm pulling them, and even when a crack starts to form, there's still noodles going across it, right? So you can think of it kind of like that because of the nature of polymers, that it's a bunch of squiggly chains of things all bonded together all over the place, some of them are going to bridge the gap, and that's going to give you an inherent increase in toughness. Now, there's plenty of brittle polymers out there. Acrylic polymer, acrylic glass is actually a polymer. You can snap that with your fingers. You've all done it, right? There's brittle polymers out there, but some of them tend to be somewhat high fracture toughness, okay? All right, there's something called impact fracture testing. If you want to actually measure something like fracture toughness, it's a little bit tricky to do. But there's something else you can do, which is measure the energy absorbed as something fractures. And it's actually pretty slick how they do this. You take a sample, like this pink bar, and you pre-crack it. They scribe it, right? They scribe it, and you pre-crack it by putting that sort of notch on the surface. So you could do that with a scribe, or you could do that with like a very sharp saw blade. You can do it by taking this thing and bending it just a tiny bit, and that will introduce a crack. There's lots of ways to introduce this pre-crack, but you need to know how big it was initially. Jaden? Oh, yeah. Yeah, when you cut tile, when you're doing like tile and you need to put a tile around like the toilet bowl, that's a pain in the butt. But if you take a scribe, you can actually oftentimes just snap the tile right where that scribe was. Why is that? Normally, if you take a pair of pliers and you twist on a tile, it's going to shatter everywhere. But if you pre-crack it, then think about what you're doing. You've got K1C all the way through the material equals Y sigma root pi A. So let's assume that you're applying a more or less uniform stress across your material. It isn't, but it's more or less the same. So everything has the same stress, and there's some population of flaws all the way through your material, however the manufacturer made it. But then there's one ginormous flaw on the surface, which is the worst place for it, because it's twice as deadly as in the interior. So where's it going to break? Wherever it satisfies this condition on the right-hand side first, which is on the surface. If you do it right, you'll pop that right along where you scribed it, which is a pretty handy tool. So yeah, that's exactly right. Okay? So this is not that, but this is kind of that same idea. You're making it fracture in a single spot because you're putting a big flaw right there. So what they do is they take this bar, they lay it across two supports, and then they've got this beam that comes flying in and bends it, right? And the tensile end is over here. So it puts that notch under tensile stress, and it's going to cause it to break. And what's amazing about this is the system looks like this. It's on a scale. So you raise your hammer up, and this is where your sharp little slicer is. Your sample is set right here. You measure the angle with this really precision scale. You let this swing. When it hits your sample, it's going to absorb some energy, right? Energy has to go somewhere. A little bit has to go into breaking your sample. So if some energy was used here, then this thing can't swing back up to where it started from. First off, it can't swing back up to where it started from entirely because there's friction in this device. So you swing it once without a sample in it, and you figure out the baseline. That's calibrating it. Then you put your sample in here, you swing it, and you find out what the difference is between the calibration and the final height, right, with a really precision scale. And all of a sudden, you can back out an energy. If you know the weight of this thing and the height, you can actually turn that into an energy. You can say that for some cross-sectional area, right, if this is like a centimeter by centimeter sample, it took X number of joules to fracture this thing, which is pretty slick because you can do this at lots of different temperatures, lots of different materials. Maybe you change the grain size, the size of the crystalline regions in your material. And it turns out to be a handy way to figure out the energy absorbed in a fracture, which will be proportional to toughness. Toughness, again, is hard to measure. The fracture toughness itself takes more delicate experiments. But this is a pretty cheap and easy way to get a measure of toughness, okay? So if you do this, you could take this impact energy absorbed by the sample, measure this at a bunch of different temperatures, right? Put your samples in freezers or fridge or liquid nitrogen, take it out quickly and measure it, and you'll typically see in many materials the following behavior. You'll see it at low temperature be a very low energy, and at high temperature, it absorbs a higher amount of energy. Or in other words, you're seeing a ductile to brittle transition, right? Ductile to brittle transitions, as a function of temperature, the mechanism of fracture changes. It can change as a function of temperature. And so the energy absorbed can also change. And this was why in World War II, when we started, Pearl Harbor happened and we lost all of our boats. So the United States freaks out and we start making ships like crazy. So we created these Liberty ships, is what they were called, I think. Yeah. World War II Liberty ships. They manufactured them not up in the cold, North Atlantic Ocean. They manufactured them at with whatever steel they had. It was all fine where they manufactured these things. And then when they get them up into the cold waters of the North Atlantic, your steel did something like this. It went from this to that, right? And all of a sudden, these ships, which were just fine, start breaking in half. Like stuff that looks like it's out of a comic book, like Superman just snapped that thing in half. Because engineers didn't know, because we were freaking out because we had just lost our entire Navy and we had to do something. But we didn't have the time to think through this or test things, and so a whole bunch of boats got made that weren't very useful in cold water. Okay? That's ductile to brittle transition. Okay, any questions on this so far? Anything I've covered? We all good? Feeling good about impact testing? Isaac?
Are there materials that don't, is there always going to be that curve?
No. Take a look at copper at the very top. It's hard to see. It's that dashed orange line. Some materials don't exhibit a ductile to brittle transition. It's not like it's a fundamental thing that will happen and you can find it. Some materials are resistant to it. And some, it's a small difference, right? Take nylon. Nylon, it is more brittle, but it's not as big of a difference as, say, steel, which is a big difference in energy. Okay?
And then would it ever be opposite and get more ductile?
There might be an example. I can't think of one offhand. So if it's out there, it's obscure. It might be out there, though. All right, let's switch gears and talk about, or were there other questions I can answer? Yeah.
So if it increases in energy absorbed, that means it gets more.
Yeah, so if it took more energy to snap that thing, so the thing swung down but it didn't go up quite as high, that means that more energy was absorbed, which means that this was more resistant to fracture, so it had a higher fracture toughness, right? Had a higher fracture toughness because it took more energy to fracture it. Something else that can happen is called fatigue. Another wonderful material science term. We're all feeling it. A semester, a third of the way into the semester. Fatigue is exactly what it sounds like. It's like your material gets tired, and after some period of time in use, all of a sudden you get failure. On day one, you don't get failure, but after some period of time, you get failure. So what's happening here, right? So fatigue always has to do with this idea of cyclic loading. If it's under a constant load and it fails, it's a different mechanism. That's creep, which we'll talk about later, right? This is cyclic loading. So what can cyclic loading come from? Maybe you've got this pencil, and I'm rotating it, right? But what if instead of just rotating it, I bend it just like a half a degree, and then I rotate it? Now, like the top and the bottom are rotating between, at this point, like the yellow thing, right? The top side of the yellow thing is under tension. The bottom's under compression. If I switch it, it's the exact opposite. So it could be a nice sinusoidal transition like that. So in your car, right, drive shafts, if they're not exactly lined up, there is stresses in them. So what will that do over time? It might cause fatigue, which is failure due to a cyclic stress over time, okay? My hillbilly brother builds these monster trucks. How do I look for it? Sparks Motors 6-wheel truck. Like, they build these massive creations, and they've had a bunch of these things which they've sold come back, and the shaft surrounding the transmission is actually breaking because it's just vibrating a little bit because they haven't got it exactly dialed in because they're making this up as they go, right? And it created just enough stress that these things are actually fracturing. But it's not on day one. It's 3 months after the customer spends $200,000 on a truck like that. And then they have to figure out what on earth went wrong and how do they fix it. Okay? So there is cyclic stress, and that can be about zero. So in this case, when I rotated it, it's its average stress is 0. But you could also have an oscillating stress where the average stress is not 0, right? Maybe I'm pulling on this thing at some strength, and I'm oscillating how hard I pull on it, but it's never 0. Therefore, the average is always greater than 0. It's always under tension as I'm pulling on it. I'm just changing the frequency or the amount, maybe. That would be a cyclic stress. Or maybe even it's due to, like, random loading. What might this be too? What about, like, daily temperature swings? In the real world, we exist at temperatures that fluctuate. And when things fluctuate in temperature, they expand and contract. And that expansion and contraction could be causing stresses which are, they have like a 24-hour rough cycle, but the actual values could be kind of noisy, right? However your data is coming from, your stress, this can all lead to fatigue, okay? So because of that, we have this really slick thing where some materials exhibit a fatigue limit and some don't. So here's what I'm talking about. You see this plot. Here we're showing you the stress amplitude. What's an amplitude? An amplitude is if I've got an alternating stress, something like this. What's the amplitude? Yeah, it's like peak to trough. That's our amplitude. Okay? Okay? So the amplitude, that's what is plotted here on the y-axis. So if this is offset from 0, you could still have the same amplitude even though this whole thing's offset. Okay? As a function of number of cycles, NF. And take a look at this. You see some materials like steel exhibit what's called a fatigue limit, whereas others like aluminum have no fatigue limit. So what is plotted here is, this is let's say that we stay at 300, right, megapascals, meganewtons per meter squared, I think that's megapascals. We're at 300 megapascals. This tells me that how many cycles can I survive with aluminum? This grade of aluminum can only survive 10 to the 4th cycles and it will fail. Whereas steel will last 10 to the almost a million cycles, almost 10 to the 6th cycles. Now if I do the same exact experiment but I lower the stress to 200 for my amplitude, take a look at this. Aluminum will fail at a higher level. It'll last, almost like 500,000-ish or so cycles. But steel will never fail because it never intersects that line. This is because steel has a fatigue limit. It has a lower limit to which it will fail due to cycling. This is pretty awesome. If you have an application where it needs to be cycled many, 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 many times, let's say like the drive shaft that's going to be rotating and undergoing some sort of stress on a vehicle, do you want to make it out of aluminum, which is lightweight, which is great for gas mileage, but exhibits a fatigue life where it's just going to get weaker and weaker over time and eventually snap? Or are you going to do it out of steel where you can engineer it to never exceed some fatigue limit stress so it shouldn't ever break barring something nutty that happens, right? It's pretty obvious what you do here, okay? So that's a fatigue limit versus not having a fatigue limit. Yeah, question?
Why don't some materials have this?
So it's a good question. What do you think? Why would some materials get weaker and weaker and weaker over time and others don't? We haven't talked about it yet. In a few chapters, when we get to deformation mechanisms, 5 chapters away, we'll talk about what happens when you deform a material. There's things called dislocations. Like if there's like this nice perfect arrangement of atoms, if I mess it up by like I've got this whole section of atoms, if I bend it, I'm going to mess up the perfectness of that crystal. That's called a dislocation. Some materials, those dislocations keep on piling up and they make it more and more brittle. Other materials, they're able to recover from that. Steel is able to recover from that. It doesn't have a cumulative damage effect, whereas aluminum does. Okay? So, yeah.
So it seems like the amplitude only cares how much the difference
Yep.
between the stresses is.
Yep.
So even if you have like a lot of stress but the difference is small, it
Yeah.
can fail.
That's confusing, right? That's unexpected. Because you're equating normal stress when you bend something, it's the maximum stress that causes the right-hand side of the Griffith fracture equation to fracture here. But here what's happening is something different. This is fatigue, and we're going to talk about what's going on in in a few minutes. Okay? So we'll come back to it. Now this is showing some average failure, right? You might have, if you have 100 samples and you test all 100, do you think they're all going to fall right on that line? Of course not. So a better version of these stress versus amplitude cyclic fatigue plots would have the following. It would have maybe like 1% failure and 99% failure. So you know the rough bounds. And some responsible plots will have that, right? Some sloppy ones will just have an average. And you're left to wonder, like, what's my distribution? If I can't have 1 in a million, even that few fail, how many cycles can I really go to? Can I go to 10 to the 4? Can I go maybe 10 to the 5? You're left wondering. A better plot would tell you that at this point, 1% of your samples fails. At this point, maybe 20%, 50%, 75, 100, something like that would be a more effective plot. So as you guys go out and get jobs, think about that, right? And make those plots if you end up making these things, okay? Okay, that's variability. Okay, how about this? Turn to your neighbor and tell him, why do you think some materials, like polymers, tend to have a strong dependence on frequency when it comes to fatigue, whereas others don't? Frequency is just how quickly the change is happening, right? If you're alternating on this pencil thing between compressive stress and tensile stress, it might depend on how quickly I spin this thing. That's the frequency. Why should polymers be affected, but metals maybe not quite so much? Jaden?
Does it have to do with, or so you said, like steel has no way to recover? Does it have to do with like rate of recovery?
Yeah, sort of. Polymers, how do polymers deform? We'll talk about it in a few chapters, but basically these chains of polymers start to slide past each other. And what happens is as they're sliding past each other, you're basically putting it under tension so they're sliding, compression so they're smooshing back together, sliding, smooshing, right? And you end up with it heating up a little bit, right? And in polymers, when you heat it up, because they melt at such low temperatures, then you transition from a different deformation mechanism, basically. So metals and ceramics melt at much, much higher temperatures, and so they're not as prone to this problem. Okay? Hence, polymers are more likely to be frequency dependent. So yet another thing you have to account for. Not just strain rate, not just temperature, but now frequency dependence if you really want to get this thing right. Okay? Okay, fatigue always has, we mentioned this at the beginning of the chapter, it's always got two events. The crack has to be initially formed, and then the crack has to propagate. Okay? So we could calculate the total number of cycles would be equal to the number of cycles associated with initiation and propagation. Right? My pen turns back on. Okay. Right, you've got initiation and propagation. You can, in some cases, see in this steady state crack growth regime, or in other words, there's a region of time where the crack growth is very predictable, which we'll show you the equation for in a moment. But as you stress it, you'll see these sort of things happening. If this is your initial crack in that top region here, when you first start pulling on it, say under tension, you're going to elongate that crack a little bit. And then as it goes back to compression, it's going to squeeze back shut again. And as it opens and closes, you're left with these sort of little ridges on the side as it undergoes each cycle. So you could technically go back and count these things, right? You could count those if they were visible on the fracture surface, and you could figure out how many cycles did it take before this thing failed in that regime. Believe it or not, you can actually see these on things. They'll call them benchmarks, striations, or clamshell patterns, right? So this was your initial crack right there at that tip, and you can see these sort of grooves representing each cycle. They grow outwards until this total flaw size from here to here it satisfied the right-hand side of Griffith's fracture equation. Once your flaw was that big, all of a sudden the fracture toughness of the material wasn't big enough, and the whole thing broke spontaneously. It didn't take additional cycles for it to break. It snapped at that point. So this was, I think, one of the questions, like, how do these things, why wouldn't it break on the first high cycle? Because this crack is slowly growing over time. And you can see these. You could count these things up if you wanted to and actually back out how many cycles in this region actually occurred. And you could actually measure the distance between them and figure out the incremental crack growth rate, right? Which is pretty cool. So there are ways to model this. And crack growth typically looks like this. So here's our crack length on the y-axis. On the x-axis, we've got your number of cycles. And you've got three different stresses here, right? Each one of these three different symbols represent different stresses. Which one do you think is the highest stress? Yeah, the smallest one. Why is that? The crack grows the fastest under the largest stress. So that would be something like stress 1, stress 2, stress 3. As you change stress, in all of these scenarios, the crack is going to grow, okay? But it might grow really slowly for sigma 3, and it might grow much more rapidly for sigma 1. Is the crack growth linear? Sadly not. It's exponential, right? It's always nice when things are linear because then they're easier to model. You can say, oh, if it grew 1 millimeter after X number of cycles, and I want to know how many cycles till it grows to get to 2 millimeters, it's just double, right? But this isn't going to work like that. Jaden?
Does that have to do with leverage?
Yeah, so good question. Like if you go back to here, if this thing's being stressed, the stress state that you are putting it under, that's force divided by cross-sectional area. The cross-sectional area is changing for one thing. Yeah, that's part of the reason why it's nonlinear. In any case, the way that we model it is with this famous equation, which we call Paris' law. Paris' law, I don't know the story behind Paris, I should find out, but he was the first person to realize that the crack growth rate, dA dN, the derivative of how, basically the slope of that line at any point, that's dA dN, is equal to big A, this is a constant, times the change in the stress intensity factor. Remember the stress intensity factor? Somebody remind me what that is? What was K? K was equal to the maximum stress over some initial stress. So this is basically saying it's the range in that value, okay? It's the range in the stress intensity value raised to some exponent n. This gives us exponential growth, right? Which is what we observe. So this is the equation that we're going to use to model crack growth. Any questions on this? A and N are materials constants. You have to look them up. If you have some grade of aluminum, you would look these things up for it, and then you would be able to figure out how your crack growth rate is progressing. Okay? A and N are constants. N is typically a number between 1 and 6. A is some number. It can be totally dependent on your material. And then delta K, since it's that range in your stress intensity factor, what we're going to do is we're going to take the maximum stress minus your minimum, which the right-hand side of your stress intensity or your fracture toughness equation would now become Y, just like before, but now you have the range in stress from your maximum stress to your minimum. This becomes delta sigma. Instead of just having one stress now, this becomes delta sigma, right? It's that range in cyclic stress. This fatigue crack growth all has to do with cyclic stress, okay? So that's delta sigma, and then it's square root of pi a, just like before. Any questions? Yeah, Sam?
Frequency is not accounted into this.
Frequency is not in this. That's a great question. It's not in this. There's no frequency in here, okay? We'll talk about frequency in a minute as it kind of relates to this, okay? Now, we make a huge assumption in this class, because what was the only type of stress that we were able to account for with mode 1 fracture toughness? Is mode 1 fracture, right? Which is this picture, right? If this is your material, we're pulling it straight up and straight down, and we're elongating that crack due to tension only. Because of that, we assume that if compressive stress, that there's no stress intensity factor. Or in other words, the crack only grows when your stress is greater than 0. If it's compressive stress, where the stress is less than 0, we're assuming that it just doesn't grow. That's a major assumption in this class, okay? It's not true, but it's a pretty good guess, okay? If you wanted to get more specific, you could account for it, but we won't do that in this class. When you do this, what you'll notice, this is your fatigue crack propagation rate. So this is delta A over delta, and that's dA dN. They're plotting dA dN on this plot, and it's in a log scale against the stress intensity factor range, delta K. And in this region 2, you get nice linear behavior, which is what we want. That means we can actually model it, okay? Why on earth is this linear? Didn't I just get done saying that crack growth is exponential and not linear? Why on earth is it linear in this plot? We put it in log scale instead of linear scale. What is a log plot? Did you learn about it just because whatever? No, it's actually kind of useful. Log plots are kind of neat. First off, how do you read them? You read them by orders of magnitude. Here you've got 10 to the 0 on the x-axis. What is 10 to the 0? 1. Then you've got 10 to the 1. That's what? 10. 10 to the 2? Or in other words, every major unit goes up by an order of magnitude. The next one would be 1,000. The next one this way would be 0.1, right? It goes from 1 down to 0.1, then 0.01, then 0.001. In other words, it will never hit 0. It's just going to get smaller. 0.01 turns into 0.001 if you go smaller, okay? This is not the first time I hope you're seeing a log-log plot, okay? What do the small marks mean? Well, those are the values in between. If this is 10 right here, and we're going to get to 100, the first minor tick line, which notice these don't go linear. Like there's like a big gap, and it gets smaller and smaller and smaller and smaller this way. So this is 20. If this is 10, that's 20, 30, 40, 50, 60, 70, 80, 90, 100. The next one would be 200, 300, 400, 500, right? If you need a review on reading log-log plots, chat with the TAs, but you will need to be able to read one of these for the next midterm, okay? By plotting it in this way, this looks linear. Why on earth does it look linear? Because we started out with this. We said we had dA dN equals A delta K raised to the small n, okay? If you take natural log of both sides of that equation, you've got natural log of dA dN equals, when you take natural log of this, it's going to become natural log of A. And a property of logarithms is that if things are multiplied together, you can add them together when you take the natural log. So that becomes plus, and exponents come down and become multiplied by it, n times natural log of delta K. Okay? I hope this isn't the first time you're seeing algebra with logarithms before. If you've forgotten it, go back and review it. But that's how you all of a sudden can make this look linear. Why does this look linear? Because the y-axis right there, that is our y-axis. We've plotted on a log scale, right? This was dA dN, but they plotted it on a log scale, right? So we're covered. And the x-axis is a log scale of the stress intensity factor, right there. That's our x-axis, right? So all of a sudden, we can make this look like y equals mx plus b. The slope is going to be this n, this material constant n, related to the crack growth rate, right? And then b is going to be natural log of this other constant, a. Any questions? Yeah, Jaden?
What changed it in the first stage and second or third stage to not?
Oh, okay. So when cracks first start growing, they just don't grow linearly. It's not what we call steady state fatigue. Steady state means that it's not changing with time. It's predictable. And in mode 1 and mode 3, right before it fractures and right when it's first starting, it's just not linear. But there tends to be a pretty big regime where it is linear, which is great because let's say that we call up QTI and they tell us that a flaw is such and such a size. We could then do the math if we had the constants, and we could say, okay, it's going to be another 500,000 cycles before this thing fractures. So we can either use it or we can't. Maybe need to replace it. They do this all the time. On airplanes, they literally take ultrasound measurements of the hulls of airplanes, and there are cracks in every plane that you fly in. There's cracks. They're just not critical yet, and they can monitor roughly the rate at which they grow, so they fly it until it's not safe within some tolerance factor, then they swap it. Nobody looks horrified by this. It's semi-horrifying, right? Yeah. Sorry, one more time? It depends on how deep you score it. If you score it deeply enough, maybe you're already going to be in this second regime. I'm not going to give you any of the tools to model Region 1 or Region 3 in this class. All we're going to do is some examples in Region 2. This is just an intro course. Okay? So it gets better or worse, depending on how you like it. But this is a differentiable equation, right? dA dN, I can rewrite it like this. Our same equation which we had before, dA dN equals A times delta K raised to the n. I can separate the variables. A little trick you saw at some point in calculus. I can separate the variables and get dA and dN on different sides of the equation, right? And that allows me to take the integral of both sides of the equation. If you've got dN alone, like this, then what's the integral from no cycles all the way to the cycles till failure of dN? It's just n. It's nf. You plug in nf. It's the number of cycles until it fails. So the number of cycles until it fails is right here. Any questions on that? This look vaguely familiar from calculus? And then if you take the derivative on this side, it's not going from 0 to nf, because now we're taking the integral with respect to the crack size. So instead, we start with our initial crack size, A naught, and we continue it until the critical crack size, A sub c. Where do we get A sub c? Yeah, from our friend Griffith fracture toughness. We say, okay, if you know some maximum stress, you would plug in, as it's cycling, the stress is going to cycle. When's it going to break? Is it going to break at the bottom of a cycle or at the top of a cycle? It's going to break at the top of a cycle, right? If it's an oscillating stress, it's still going to break at the top of that oscillation. So you plug in your maximum stress here. You know what the fracture toughness of your material is. You can solve for now a critical crack length. When it reaches this critical crack length, it's going to snap, okay? So this is pretty slick. You could say, if I wanted to solve for the total number of cycles for it to fail, and we're skipping the crack initiation portion, this is all crack growth cycles, so it's an approximation. But assuming that the crack's already initiated, I can solve for how many cycles until this thing fails. I need to know what A and N are, my crack growth constants. I need to know the range of stress, and I ignore anything compressive. So we're only looking at positive stresses. So I've got my range of stress. I need to take this integral with respect to A, where this is y. Why is y inside the integral? Isn't it a constant? Don't you take constants out of integrals?
It's not always constant.
It's not constant. And you're going to do that on your homework this week, which is up already. You can take a look at it. You can blame Jaden. Where is y? We have a plot up here. Here, right here. Y is a function of A over W. Y depends on A. Since your width of your sample is not changing, but the crack is growing. That's the whole point of these problems, is we're monitoring crack growth. What this means is that technically y should have to stay in the integral, and you should have to write a function for y as a function of A over W. Okay? Now, a lot of times in this chapter, for example, in the homework, in the book, they have you take y out. They say the crack is always small. It never gets big enough that you have to worry about this non-1.12 value. On one of the test questions, you will have to do that, okay, on one of them. So if we go back here, all the way down. So y technically should have to stay in the integral. If I tell you that the crack always stays small relative to the total sample width, then you could take y out. Y to the n could come out. And then all you have to do is take the derivative of dA over A to the n over 2. That's not a hard integral to take. If you need, write it down on your note sheet how to take that integral. But it's pretty straightforward, right? So you plug all those things in, and out comes a number. Maybe it's 100,000 cycles. And you know that you can last another 100,000 cycles before this thing breaks as the crack slowly grows over time. Can I answer any questions? So there's tables of these things, right? Here's a table of the n value and the A value given in normal units and barbarian units, right? For a whole bunch of materials, and you could look up other ones, right? So you can know how the cracks grow in different materials. And at the start of next class, we'll do a big, nasty example of this. Now, quick note, I will be gone on Friday. I have a dress rehearsal for a talk I've got to give on Saturday, so I won't be here, probably. So there's a good chance that I will film it ahead of time and throw it up on the YouTube, okay?